We'll have a look at a problem now where we're in salt water in port, and we're going to discharge cargo immediately, and then we're going to proceed to an upriver berth where the relative density of the dock water is 1.005. So in other words, we're going from one density to another, and the question wants us to calculate our drafts on arrival at the upriver berth. So that on the face of it, it's a straightforward weight LCG moments problem longitudinally. The little twist here, of course, is the changing densities. So let's have a look how we would solve this. Incidentally, this question can also be asked where you're initially in dock water and then you sail out to salt water. Just the reverse, but exactly the same way to solve it. So let's get our AMD first. From the tables, at that draft, get the LCF, then get the true mean draft. Of course, we minus that value because the draft aft is greater than the draft forward. Go in the tables at 8.52 and get displacement, MCTC and LCB. We need those values because we need to, of course, calculate our initial LCG. This vessel isn't at even keel. We've got drafts forward enough, so we must calculate our LCG. Transpose the formula there. The trim times MCTC over displacement value we must subtract from the LCB because LCB is greater than LCG when we are trimmed by the stern. So it comes out at an LCG of 68.21. Remembering we only go to the same number of decimal places as the tables, we can't be more accurate. Just one point I want to make here: the trim, of course, is in centimetres, so don't forget in this formula you must put the trim in centimetres. So now we've got our initial displacement, LCG moments, there's the cargo we've discharged, and then here's the oil, freshwater that we've used up going to the other berth. So all these are minus values, moments minus, therefore we found our final LCG of 68.33. Now the problem here is, of course, we're now in dock water. So with our displacement, which of course doesn't change, we divide it by the density, and that gives us our underwater volume. So what changes is the underwater volume. We then use the underwater volume in the fresh column, the density 1 column, because that freshwater column is also underwater volume, meters cubed. We go in with 17,620 meters cubed and we get the true mean draft, LCF, LCB, MCTC, freshwater, multiplied by the density to get our MCTC. Now we can work out our trim the traditional way. We get 91.1 centimeters. LCB 69.37 is greater than LCG 68.33, so we're trimmed by the stern. Usual formulas to get the trim effect aft. Subtract that from the total trim to get the trim effect forward, and therefore we can calculate our final drafts. So the twist with this one really is the changing density, but really you should be okay with this because we simply divide our displacement by the density, which gives us the underwater volume, which we go in the tables with. So don't forget, we go in the tables with this value here, 17,620.